right. So far we've been working with these spreadsheet-based numerical simulations, and now today we're going to introduce how to do this in Vensim and an Insight Maker. So I'm going to start with this kind of toilet example, which is your kind of latest homework assignment. You've been done to do it, has to do in a spreadsheet. And then in the last homework assignment before the midterm, which is officially released today, you'll be asked to build this in Vensim. But there's going to be gratuitous hints to the spreadsheet implementation in the slides to come. And towards the end of this, gratuitous hints to how to build it in Vensim in the last couple slides here. So keep an eye on that. The basic system here, we've got the back of a toilet. So here's our toilet here. Here's the tank that fills up with water. And so that water is the water that's used to flush the tank. And so in order to be ready for the next flush, it always has to have a certain buffer of water in here that empties out at the flush and then has to then refill at some slow rate. So there's always a water level in the back. And there is a target water level, which is effectively set by this little float here, that when it floats up to a particular height, it can turn off a valve. And so there is this valve that's controlled by the float, which affects the amount of water coming in. So effectively what the valve is doing, or what this float is doing with this device here, is it's sort of creating a tank gap. Like it's sort of saying, what is the gap between reality and what we want? And so it always wants target water level to be in the back of the tank, and it measures that reality, and then it uses a balancing feedback loop to drive water into the tank to bring the water level up. That's the idea there. So if we look at all of that action, this is that balancing feedback loop. So it's this simple example of where we've got this water level down here. And as the water level rises, the tank gap gets smaller. But if you have a large tank gap, then the water level is going to, because the valve is turned on, is going to start rising faster. And if somehow you change the target water level, so a lot of times you can go into a toilet and you can adjust, you can kind of screw this bulb higher up or lower down on this arm, and that allows you to change the target water level. So if you were to increase the target water level, that would make an increase on the tank gap, but it doesn't sort of change the balancing feedback loop. That's just between water level and tank gap. So this is a high level description of what's going on. It doesn't really tell us about the dynamics, like the valve doesn't really show up in here. So if we really look at this toilet, you can say, well, the flow of water, that's what, you know, this float here, adjust this valve, which is effectively controlling the flow of water. So really, if we want to get a dynamical model of this, we need the flow of water to be explicitly modeled in there. So we're just going to introduce it as an important variable, because we know that you can't change the water level without changing the flow of water. So that's what we need to add to that. So what we're going to end up seeing is that water level will be a stock because it's changing over time. Flow of water will be the force causing it to change. Well, thus it's a flow. And these things will sort of be converters, which help us build the math to make the flow work. The flow makes the water level. So this is our basic causal loop diagram for what's going on in here. And we're going to use that to build a dynamical model of the toilet. And so the way that will end up looking here is we take that water level and I say we make it a stock. We take that flow and we do the flow here. So this thick line means it's the thing responsible for changing the water level. The fact that it's going in means that as the flow of water is positive, the water level tends to increase. So that's the difference between inflow and outflow, is that when this thing is positive, it will cause this to increase over time. If it were an outflow, if the outflow was positive, it would cause this to decrease over time. The water level is used to calculate tank gap by subtracting off the target water level. In other words, target water level minus water level gives us tank gap. And then that difference is what drives the flow of water. So this is closer to a dynamical model of what's going on there, for to model what's happening over time with the filling of that. So somehow inside this stock and flow diagram, we need to put equations in for tank gap and for flow of water. But once we do that, we should be able to simulate it in either a spreadsheet or in Vensim or in Insight Maker. So with that in mind, so we can kind of keep an index of everything here if we want to sort of apply that to our kind of spreadsheet template for these stock and flow models. And so again, what are all our stocks? Well, water level is our stock here. It's also called a state variable or an accumulator or a level or a box variable. These are all names for stocks. Our converters, which are just auxiliary variables that help make the math cleaner in the expressions, our target water level, which is just a constant 15, and tank gap, which will just be target water level minus water level. So it's like 15 minus the level. And then the flows are the things that are actually causing the water level to change. So the integral under the flow is the water level, or the derivative of the water level is the flow. In this case, our flow is the simple flow of water. And then we've got these links that we've put on here, which help us show how things are related. And they work exactly the same as they did in causal loop diagrams. Now, in a stock and flow diagram, sometimes it's not possible to associate a polarity to them. So in that case, if it's sort of an informational link, like it might be the formula for tank gap doesn't have a clear relationship to water level. So for certain levels of water level, there's a positive relationship. For other levels, there's a negative. Kind of like in that fish regeneration curve, at certain densities, there was a positive relationship, and in other densities, there's a negative. So you're not always able to label the links plus and minus. If you can, that can help with the reader understand what's going on. But those are auxiliary things. You don't need to put those in stock and flow diagrams. We just sometimes do to help us recognize feedback loops and their polarities. So whenever we do a stock and flow diagram, as you'll see in Moorcroft, because you'll read the chapter for Tuesday, is that you always couple a stock and flow diagram with its equations. Now, the diagram, hopefully gets like all of the really salient features about the system to the reader. But if the reader needs to really know the details, what is the formula used for tank gap? What was exactly the target water level, et cetera, you need to have those formulas nearby in a caption somewhere or something. So whenever you draw a stock and flow diagram that is meant to be simulated, you're also going to need to have a list of expressions next to it. And those expressions are typically going to have the formulas inside the flows, the formulas inside the converters, and I don't have it here, but also the initial conditions for any of your stocks. And then you often put the time step, the DT value, which we'll talk about here in a second. So this is most of those here. The target water level is 15, the tank gap, there's the formula, the flow of water, there's the formula, just copies the tank gap. And I've added in units for these just to help the reader see that tank gap is centimeters and flow of water centimeters per second. What's nice about the units is it can also help me debug my logic to see if I might have left things out. So some of you might notice that tank gap is in centimeters, even though flow of water is in centimeters per second. And so it seems like there's something wrong here. And we will see that we are missing one little thing that we're kind of assuming is equal to 1. And so we don't worry about it at this level. But when we get to a little bit more advanced model of the toilet, then these units will match up again. So right now it is a problem in the formal sense that flow of water is expecting centimeters per second, but it's taken a variable that's in centimeters. But for now, don't worry about that. But definitely include the formulas. And then, like I said, the other formulas you need to include are the initial water level, 0, and the time step. So you always sort of have this diagram and this level of formulas. And so this stuff down here, this is what you always should have together. You never really present the stock and flow diagram without these nearby. You don't have to make these focal because they're kind of distracting, but you do. If you have this and these things, then anybody can take your diagram, draw it themselves, and reproduce your results. And that's what we really care about, is reproducibility. And you can't reproduce the results unless you've got both the diagram and the formulas. So before I go into seeing how this is implemented in the spreadsheet, are there questions about any of this so far? The water level being a stock, the flow of water being a flow, any of these formulas? Okay. Any questions online? Okay, good. All right, so this is what we would like put in a report or something, or if we were, writing a paper on, the right optimization of toilet tanks. This is what we would put in the figure in the paper, and then maybe an appendix. We would have these formulas, but then how do we actually implement that to get the graphs out? Well, if we did in a spreadsheet, then we can take this formula again. If you give me all of this and all of that, I can reproduce your results by myself. So I can look at this, I can identify the stocks, the flows, the converters, and all the formulas. And now I can build a little spreadsheet model. This is assignment D2, basically here. So, this is me kind of walking through those steps. So you'll have to do a little bit on your own, but this is giving you a good start of that assignment where I'm asking you to basically simulate this, where the bonus is you also add a leak coming out of it, which I won't show you how to do that, but this is basically showing you how to get through that assignment. So it's very similar to the bacterial flow case. We start with a DT up here, but then instead of having lifetimes and average times between births, our main static converter variable here, our exogenous variable, is target water level. So we put that up here, and there's no W or L or anything like that that's in the bacteria. We put that up here. And then down here, we set up our initial row, so our time zero row, where we put our initial condition for water level, and we start calculating formulas. So we know that before we can put in the flow of water formula, we have to put in the tank gap formula. So the tank gap formula is just going to be the target water level minus the water level. So both of those are in column B here. Target water level has got the dollar signs around it. It's just this exogenous variable here. And then the actual water level for this time step is right here, B5. It's just the current row, that column, and that gives me this tank gap. So that helps me calculate this thing. And so what we're going to do in a second is then put tank gap into the flow, and that will be the things that are specific to the toilet. The rest of it will be generic, it applies to any stock and flow model. So any questions about this so far, that this tank gap or the setup of this or where we're going? This makes sense so far? Okay. All right, stop me if I get going too fast or anything like that. I want to make sure everybody's on board. So, so the next step, we got a tank gap. So we kind of follow, water level to tank gap to flow of water. Now we have enough information, we can put in the flow of water formula. And the flow of water formula is easy. It's just a copy of tank gap, the way we've written it. So if I look up here, tank gap is equal to this. So it's like target water level, that's B2. Tank gap, that is D5. And I calculate that by doing B2 minus B5. That's what went there. And then now that I've got tank gap, which is D5, I can just put that directly into flow of water. Flow of water equals tank gap. Well, here's flow of water. You go to D5 there. And so I can fill that in there. And so that, now that I've filled out all of the flows, then this row here is all, or these two images capture all of the formulas that are specific to the toilet. What I'm going to fill in down here are filling in the stock formulas. And the stock formulas are going to look exactly like the bacteria stock formulas, because stocks evolve the same way regardless of the system. What changes from system to system are the flows. As long as you got the flow formulas, then the stocks just move along like that other system. So the flows configure the system. So any questions about either of these two formulas here, the flow of water or the tank gap? And we can see initially the tank gap is going to be 15, because that is going to be 15 minus water level. And that's what gives me an initial gap of 15. Okay, questions online? Everybody good? Okay. All right, so now we can do our generic stock update formulas. So time is sort of like a stock. So it has a very similar formula to a stock update. It's just the previous time plus the time step. So that's what we got there. So if we're to think about calculus-wise, if you think about time as a stock, then the flow of time is like dt equal to 1. So if you think about this, this is exactly a stock update formula for time. It's like time plus its flow, which is equal to 1 times dt. So that's where that kind of comes from there. And then I need to actually update the water level one, and that's the more generic version of the stock update formula, which is just the previous water level, B5, plus C5, which is the flow from the previous time step, times our DT value, which we've set up here as 0.01. And that gives us our water level flow. And those are all of the formulas we need to simulate the toilet. We grab the bottom rows here. We buy this guy, and these two. And if we were to pull those down, then we'll simulate the behavior of the toilet over time. So any questions about that? And why? I mean, I'm going to do it. In the next slide, we'll actually see the output from that. Questions online? And again, this is basically assignment D2. So, all right. Okay, so I fill those down, and here's what I get out of it. I have plotted, I think I only ask you in assignment D2 to plot the water level. I've gone ahead and plot the water level and the flow of water. The water level is blue. That's the water in the toilet. And the flow of water coming into the toilet from the wall is this orange color. So we can see initially the flow is high, and it goes down to 0 as the toilet settles down. And initially the water level is 0 as it's empty, but then it rises slowly and slowlier to 15, and eventually stops around 15. And so that's, I'm just plotting here time on the x-axis and either water level in blue or flow of water in orange. So you can see water level starts at 0, flow of water starts at 15, water level climbs, flow of water declines or decays. So does this plot make sense? I mean, if you think about it, if you think about flushing a toilet, it's loudest initially, and then it gets quieter and quieter until it just sort of claps off. And there's a nonlinearity which causes it to turn. And now if you really think about the math here, this flow of water will never actually get exactly to 0. And this water level will never actually get exactly to 15. So they put a little mechanical nonlinearity in the valve so that when things get sufficiently low on flow, it just snaps it and turns the water off. And that's what causes your toilet to eventually turn off. But roughly speaking, this is a decent approximation of what happens in a normal toilet, is that's why you've got kind of a loud noise up front as it's filling, and then it gets quieter and quieter. And it might get kind of squeakier and higher pitched as the flows get smaller, and that nonlinearity starts to clap that thing off, sort of pinch it off, kind of like wax or something, or like a balloon being pulled tight. So that's kind of what's going on here. So does this plot make sense to you? That fast flow initially, slow flow over time, and it kind of settles out at 15. So hopefully, so your goal for assignment D2 is to replicate this so that you get this plot. And you can do things like play with DT, see what happens. You can try playing with the water level, see what happens. And then the bonus, add a leak, just like you add a death flow in the bacteria. So that'll mean adding another flow here. So this will be the inflow of water, and then you also have an outflow of water. And you'll have to then update the stock update formulas to be, instead of just the inflow, it'll be inflow minus outflow. So if I were to go back, this formula here, it's got B1 times C5. Well, you could imagine putting parentheses around C5 and then doing inflow minus outflow. And then that's pretty much all that you'll need to do for that. So I'll pause here. Questions about that? That makes sense. Now, what's cool about this is the math here, there's a little bit of math, right? But they're relatively simple expressions. And you get this nice, smooth curve out here. If I were to go back to SOS 211 or any generic calculus course, and I were to give you this expression here, which would be, DDT water level, the change in water level over time, is equal to some constant water level 15 minus that water level. So imagine this is dx dt equals 15 minus x, and ask you to solve it, then you would get an expression that would be evaluated as looking, I thought I had the expression here. Oh yeah, there it is down here. You would end up getting this expression down here, which is the water level over time is equal to the eventual asymptotic water level, the target water level, times this expression, 1 minus e to the negative t. And if you were to plot this thing, it would be the blue line. So it's kind of a headache to get from here to here mathematically. You have to group all the water levels together. You might have some 1/overs. You might have to do a logarithmic substitution or whatever. To do this analytically requires a lot of steps and some specialized knowledge about how to solve these ordinary differential equations. But numerically, we can, for any one of these differential equations, we don't need to know the tricks to solve this differential equation or that differential equation or whatever. We end up getting the exact same curve out. The downside is we don't get the formula out, but if you were to plot this formula, you just get the curve. So if we, in doing a systems analysis problem, really only care about the shape of these curves or where these curves hit particular performance levels at certain times and those sorts of things, then this is pretty good. Oftentimes we might actually get a description of what's going on for time points that might be difficult. Like there are some differential equations that you can't get the expression over time. All you can do is find out where they're going to be as time goes to infinity. So you might be able to only figure out that this toilet eventually hits 15, but you don't actually be able to figure out where it is at time 10. Whereas when we do it numerically, we can actually estimate where it is at time 10. So it's pretty powerful, and it doesn't require a lot of mathematical baggage in order to get it done. So that's why these sim tools are so nice. So questions about this? That makes sense. Questions online? Just going to do a sort of a organization here so I can see things a little better. Okay. All right. So how do we actually build these models and interpret these expressions? So, throughout the rest of the semester, you're going to be looking at dynamical systems models that are written in terms of stocks and flows, where all of the system information will be built into the flow expression. So we need to sort of know how to interpret these flows so we can build them and so we can read them when we look at how other people build them. And so when we look at a flow here, flows, generally speaking, usually can be kind of factored into these two parts where there's some stock amount divided by some time interval, and flows will always be in units of whatever the stock units are divided by the time units for the system. So if the stock is in centimeters, the flow will be in centimeters per second. If the stock is in centimeters per second, the flow will be in centimeters per second per second. So you're always going to add a per time interval to whatever the stock unit is there. And the way we interpret this, like remember that toilet, it started out like looking like a line that was like a rocket taking off at a particular angle. So if I were to sort of draw my interpretation of that, or the toilet model, then remember the toilet kind of rose up like that, where it initially started off like a straight line, and then as the flow got kind of pinched back, then the water level leveled off. Well, the way we interpret the flow at any particular point is if the valve stayed on for that amount of time forever, then in that hypothetical case, after this time interval, we would move the stock up this amount. So when the flow is initially 15 here, what we're saying is after 1 second, the water level would go up all 15 centimeters. So, but what actually happens is that after a half a second of that flow, the flow starts decreasing. So the flow isn't constant over time. So that's why it's a little confusing, but remember, it's a derivative. It's the instantaneous rate of change of the stock. And so if the flow stayed on at this level constantly, the stock would rise this amount in this time interval. But because the flow is changing over time, that probably won't end up happening for the system, but that's how we interpret it at any instant of time. So if a flow is 15, that means a stock would rise 15 if the flow stayed there for the whole second. Or I could interpret 15 as 30 over 2, which would mean like it would rise 30 in 2 seconds if it stayed on for that amount of time, and so on and so forth. So that's how we interpret these flows. Let me get back to PowerPoint here. All right, so like, how do we apply that to the systems we've seen? Well, in the bacterial system, our flow was the number of bacteria in the system at that time times 1 over W, where W was the waiting time between reproduction events. And so the population inflow was the number of bacteria divided by the average reproduction time. So this is saying that if if that flow stayed that way forever, then every W time units, you would add number of bacteria to the population. But of course, what's happening is that once you add a little bit of bacteria to the system, they start reproducing and the flow rate goes up. So in the next instant of time, the flow goes up. And so it doesn't always stay constant, but the way we interpret it is for that instant, who's contributing to reproduction? At that instant, only the currently alive bacteria are contributing to reproduction. And this is how high, this is the hose is turned on at this amount. But it's kind of like if your hose was turned on and as it's filling the bucket, there's like a sensor seeing as the bucket's being filled. If it were to turn the hose on even more based on how high the bucket was, then the bucket would get filled faster and faster and faster, and that's the exponential growth of bacteria. So that's how we interpret this particular flow expression. If these number of bacteria were the only ones ever reproducing, then bacteria population would grow linearly, where they would add this number of bacteria every W time units. But because new bacteria start reproducing too, they grow non-linearly, and that's the exponential growth that we see. But at the instant of time, we approximate them with linear growth, and this is the rate of change for the linear growth. So does that make sense what I mean by flow in terms of bacteria? It's a little abstract, but so when we form these things, we often ask like, oh, this is a growth problem. Well, what's the current flow for this growth problem? We could say, well, we want to sort of know what's the average time until we get a reproduction event and how many things are reproducing. So these are how many things are reproducing. This is the average time to reproduction event. That is the typical flow when we've got a growth problem that we're modeling. And it could be growth in police in a city. It could be growth in students anything that where the number of individuals ends up creating like through reputation. The students really like the school, and so with more students at the school, you get more new students at the school. Then we can kind of model it this way. Okay. So, and this is just me kind of saying, summarizing that here. So if we waited for average time to reproduction, each of the current number of bacteria would reproduce, and there would be number of bacteria, more bacteria. So the population growth rate is the current number of bacteria divided by the average time of reproduction, exactly what I just said. So likewise, the death flow, we think of the same way. And we are to sort of say that bacteria deaths per unit time at that instant of time, then this many bacteria are each contributing 1 over L to the outflow of deaths. And so the population death rate at an instant are the number of bacteria divided by the average lifetime. Now, that's as bacteria start to die, the death rate will be reduced because there'll be fewer bacteria dying. But if somehow we could constantly be pulling bacteria out at this rate, this would mean that we could eliminate that in average lifetime, we would actually kill all of the bacteria. So like at exactly average lifetime, all of the bacteria would go away. And that's not going to happen because the number of bacteria, basically if we're going to plot the bacteria curve over time, we have some number of bacteria. And this approximation, the flow might look like this, where this is W. And this is saying that for some number of over W unit time, if this death flow stayed constant, these bacteria would all be dead in W time. But in reality, what the curve looks like is more like this, where it starts off at that flow rate, But as you get more bacteria dying, then there's fewer contributions to death. And so the bacteria end up sort of dying off slower than would be expected if this was a straight line. So that's what we're kind of saying. What is the rate of change at this instant? And it's going to typically be, again, the number of individuals causing that rate of change divided by the average time in between events per each individual. That's how we write that flow. Does that kind of make sense? At least start to be kind of murky. And again, the units are always going to be stock divided by time, bacteria per second, for example. Okay. So the guidelines here for these population type systems is that we measure the average time it takes for an individual to be added to the stock. This is for growth, but for death, it'd be also to be taken away from the stock. And the contribution to the inflow rate for each individual will be 1 divided by that time. And then so the contribution for the whole population will be however many individuals there are times that 1 over time, each one of their individual contributions. And then you get rid of the 1 and it just becomes individuals divided by time. So, so that's how we get for the inflow contribution. The outflow can be written the same way, where every individual is contributing 1 to the outflow per average time, whatever that average time is. So the outflow will be number of individuals divided by that time. So if it takes W time units for them to be born, then the inflow will be individuals divided by W. If it takes L time units for them to die, then the outflow contribution will be the number of individuals divided by L. So in any case, it's, the units help you here because it's not times W or times L, because you always want it the number of stock divided by time. And that kind of gives you a hint that if you know W and L, you're going to do number of individuals divided by time. So does that make sense for these population type systems? General guidelines for any time populations are growing or declining. All right, and then we got the other types of systems like this, these kind of balancing systems where it's harder to think of them as growth systems. And so how do we interpret the flow rates here? Well, I kind of talked about this already for the toilet. If the valve is maintained at this flow for 1 second, the remaining tank gap will be filled with water. So this is the flow of water that we implemented inside the spreadsheet. Now remember I said it should raise some red flags to those of you really paying attention that flow of water should be in centimeters per second and tank gap was in centimeters. And here's where it comes together. There's a hidden 1 that we don't have implemented in the spreadsheet because it's just divided by 1, but where we are making the assumption that the valve has been configured so that it pumps in water at this rate of 15 centimeters per second when the tank gap's equal to 0. And so if we bought another valve from the hardware store, it might have a different rate here or a different time here. But so we, for simplicity, I just said, let's just set it equal to tank gap exactly. But by setting the flow equal to tank gap, then what I'm saying here is that the flow is so high that after 1 second, the entire tank gap will be destroyed if the flow were to stay on that amount. Now, in reality, the flow is going to get pinched off very quickly as the water goes up, and that's going to cause the tank gap to take longer than 1 second to get automatically filled. So that's what I'm saying here. Because the valve rate's constantly changing, the tank gap will never actually be reduced to 0. But if it were left on at this flow for the whole, for continuous time, then after 1 second, we'd close the whole tank gap. So, so that's kind of what we're going there. So for these types of systems, so bucket-like stocks that empty or fill and then stop, the way we choose our flow expressions is that the inflow rate is typically written as the gap size at any time. So, if we're thinking about the flow, just if you have the gap in your system, it's gap size divided by T, where T is, and this is where it gets a little weird, it's the average time it'll take for closing the gap by this weird number, 63.21%. And that's not an arbitrarily chosen number. We'll learn about that number a little bit later as we go. And I think I say here, sometimes this is called the so-called time constant of a system. So it's just for convenience that if you do the math on these types of systems, then someone figured out, like, ideally, I'd like to know how to write this formula as this simple expression, gap size divided by T. How do I figure out that T by looking at a real toilet? And they figured out that well, if you measure where the time at which the toilet is filled to 63.21%, that time will correspond to exactly this time here. This is like a half-life, but it's sort of been it's sort of been extended. It's not exactly a half-life. A half-life would be like 50%. That would be like the time until you've closed at 50% of the time. But if we were to choose that time, then this expression would be uglier. There'd be like natural log of 2's in here somewhere. So in order to make a nice clean expression as your flow, where it's just gap size divided by T, then this tells us we look at the real system, we measure where they hit 63.21%. So it's kind of like, let's say you go to a hardware store and buy a bunch of different valves, and you like to simulate each one of them. Well, you could install each valve and in a toilet, and you could then flush it and then set a stopwatch so you could paint a line on the tank. And when it hits 63% of the total fill, 63% of 15 centimeters, then just record that time. And in that time, for each valve, so for some valves, it might be 5 seconds. For some valves, it might be 1 second. That would be the time constant for that valve. And that represents kind of the stubbornness of the system. And you can put that in your simulation, and that helps you calibrate your simulation to the actual valve that you've bought at the store. So, so that's kind of how we match data to these sims with this so-called time constant. All right, so so for our system, does 1 second seem like a normal consumer time constant? I would say that's probably pretty fast, because after 1 second, I don't think the water in most toilets goes up more than half of the tank, 63%. So if we were actually simulating a real toilet, I probably wouldn't have given you the expression flow is equal to tank gap. I would have probably given you flow is equal to tank gap divided by 20 or something like that, which would mean that after 20 seconds, it goes up 63%. So, but this, just for simplicity, I said flow is equal to tank gap. And that implicitly was telling you we're modeling a really fast toilet where it closes the gap 63% in a second. So does that make sense for these kind of bucket-like problems? When I say bucket-like problems, these are problems where they're balancing loops that eventually settle out to balance themselves out. And this time constant is 63% of how long it takes to get rid of any disturbance. Okay. Questions online? Yeah. Yeah, if you want this nice formula here, where it's the stock amount divided by the time interval, in this case, in these negative feedback loops, it's typically going to be gap size divided by some parameter t. If you're trying to figure out what is the level, this is an exogenous parameter, so I got to get it from somewhere. I got to sort of set it by looking at data in the real world. Then the way we do that is we do what's called and we'll talk about this more, I think, just after the midterm, but we do what's called a step response. And what that means is we hit a system with a sudden step we go say, here were what we were desired before some time step, and then at some magic time step, we increase the desired, what we desire. So in this case, the toilet, it's like suddenly, at the time we flush, we suddenly desire it to refill 15 centimeters. And then we just measure in the real system how long it takes for it to come back to that desired level. And then we just set that T to be the 63.21%. And so if the formula is this, then that's the one we get. Now, there are some, say, physicists out there who are more accustomed to thinking in terms of half-life. And so when they build their flow expressions, they might actually write this expression with, and like you'd say, you'd see a bunch of natural log 2's and this sort of thing. And in that case, they would know that, well, actually, I want to measure the time until, let's say they're measuring the decay of some radioactive substance. Well, in that case, they would say, well, how long until I get 50% of the substance? And that would, they plug this in here, but you couldn't plug that into this formula because this formula isn't designed for half-life. If you did that, again, you would need extra parameters to scale that. So this is just a scaled version of half-life. And in our systems, it's easier to, I would rather not have a bunch of ugly natural logs floating around in this formula. And so the downside of that is I have to choose an ugly percentage. But if I wanted a clean percentage, like 50%, then I would need some ugly other parameters inside here. Does that make sense? A little abstract. Any other questions? Okay. And I can actually show you where this 63.21% comes from. It's actually related to e to the negative 1. So this is basically, if you're wondering, if you were to calculate, this 63.21%, if you're interested, that is 1 minus e to the negative 1. So Euler's number is whatever around 2.7. So if you do 1 divided by 2.7 and then do 1 minus that, then you should get something around 63.21%. So where this comes from, I could go back and show you, but for time, I'm not going to really worry about it. It's kind of outside the scope of the class. But if you're to go back and look at the formula for how the toilet tank fills, then you might be able to figure out like, oh, okay, so I see where T shows up in that formula. If I want to solve for T, then what time sort of makes T pop out nicely, then it'll be the time associated with this percentage, this 1 minus e to the minus 1. So that's where that weird number comes from. And I just remember it as like, I start with 6. I remember it's roughly 60%, and then the rest is just 3, 2, 1. So I know it's 4 digits. It starts with a 6, and the bottom numbers are 3, 2, 1, and there I memorized the whole thing. So it's just sort of a common, one of those numbers that you just learn to memorize over time. All right, any other questions about that? Great. All right, so that's the toilet example. So now generically, stock and flow diagrams, we want to learn how to draw those in Vensim and Insight Maker. So in any tool that any system dynamics modeling tool you go into, you'll have stocks. Again, sometimes they're called state variables, sometimes called accumulators, levels, or box variables, but the most common name in the literature is stocks. And these are 4 different programs. This is Insight Maker here, Vensim up here. I think this is AnyLogic, and this is, I think, Stella. So 4 different programs, 4 different depictions, but you kind of get the point. They're generally depicted as boxes. A lot of times, like in Stella, they actually show the boxes partially full. In Vensim, they'll actually plot the stock levels over time in the middle of them. So that's a stock. The flows are often depicted this way. So the common element here is it's a thick directional line. Very often they have little valve symbols here. This is supposed to be like a spigot, like a valve here. So if you look kind of at the top of this thing down, you can kind of see how this might look sort of like a valve. And this is in fluid dynamics, the common symbol for valve. So Vensim draws it like that. This is Stella, this is AnyLogic. And the web tool, Insight Maker, they just didn't bother with trying to implement that. So they just made a thick line instead, which I think is totally reasonable. But traditionally, it's common to depict some sort of valve. And then converters, these are just extra parameters or to extra formulas to help make the math easier. And they're often drawn as little circles or ovals. And so Vensim up here, down here in Insight Maker, looks like this. There's in AnyLogic, they look like little circles here. Stella looks like a circle. So common thing, they're just drawn as circles to differentiate themselves from stocks, which are boxes. And then links. And so links are usually thin lines, often kind of curved. Sometimes they're dashed. Sometimes they're called causal links. Sometimes they're called informational links. I'm going to call them links in this class. In Moorcroft's chapter, the chapter you're about to read for next week, I think he differentiates initially between a causal link and an informational link, but throughout the rest of the book, he doesn't really care about the differences there. What we mean by kind of difference in causal link and informational link is that some links, it's clear there's kind of a causal influence we can label, like with pluses and minuses, but others, they're just information needed to calculate a formula, but there's no obvious like up and down relationship. And so we just need it. So it's informational, but we can't say this has a positive effect on this or that. So there's maybe a distinction between causal and informational, but it's not important. So as far as I'm concerned, it's just a link. So again, thin, usually curved, sometimes dashed. Sometimes we can annotate them with plus, minus, S, and O if it's possible, but it's not necessary to do so. So in a causal loop diagram, you got to label everything, links and loops. In a stock and flow diagram, you are free to, but you're not going to get taken off if you don't. So you only have to draw the stocks, the flows, and the links. You don't have to annotate them in a stock and flow diagram. All right, so any questions about those three constructs, graphical constructs, before we do some examples and then show Vensim? Okay. All right, so quick examples here. If I'm modeling a bank, I might have my desired bank balance across all my balances. I might have all my balances, and then I might have a gap between desired and actual. Now, up here, if I drew this in Vensim, I can drill down into this gap between desired and actual and put a formula in, desired bank balance minus all bank balances. But Vensim is going to give me an error because I didn't draw any links. You can only put a formula inside a converter or a flow if there is a link going into it from the variables you're going to use in the formula. So in this case, I'm using desired bank balance and all bank balances inside this formula up here. So I need to draw those incoming links coming into there. And if I draw both of them, then Vensim will not report any errors in this formula. So I draw them to give this variable or converter access to this information. Now, because if I want my bank balances to change over time, then this isn't a dynamical model because I have no stocks. So changing over time implies I need stocks. So the full model is going to have a savings account balance, and it's a stock because it potentially changes over time by interest. And the checking account balance changes over time by salary. So that's the flow going into those two things. So the links that are definitely missing here is that, well, since I have all bank balances, I can't calculate all bank balances unless I add up these two. So that's something that's missing. I have to bring savings account balance into all bank balances and checking into all bank balances so that all bank balances can be the sum of those two. And I can't know the interest going into my savings account without knowing how much money is already in my savings account. So I have to draw that going into the flow. And this gives us kind of a minimal model of the bank. So my salary doesn't depend upon my checking account. It just comes in, weekly or bi-weekly. The interest depends on how much is in the savings. And then these formulas, so this is my goal in my head. This is the gap between those things. And so if I had another behavioral model, I could use maybe this gap to drive like my, how much spending I have on movies or things like that. So I could add that into it. So any questions about the links drawn here? Does this sort of, like, in order for me to make these formulas work, I have to draw these links. Does that make sense? Questions online? Okay. All right, so whenever we have a generic stock and an inflow, so when I'm thinking about causality, there are implied causal links that we don't usually draw, but when we're analyzing feedback loops, we have to remember they're there. So I already mentioned this before, an inflow versus an outflow. An inflow is such that if you were to increase the inflow a little bit later, you would increase the stock. So there is an implicit causal link or positive link between inflow and stock. So this implicit causal link is not usually drawn because it's kind of chart junk, because it's always there, but we have to remember that it's there. Similarly, on the outflow side of things, if the outflow gets bigger, the stock will get smaller. So this is one that's easy to forget about because the flow is pointed in this direction. But because it's an outflow, there's a causal link pointing back at the stock. So again, we don't usually draw that, but we have to remember it's there because that might complete a feedback loop. And if we are only looking at the directions of the flows, we're going to miss that feedback loop. So, so that we have to remember is there, even if we don't draw it explicitly. Are there questions about why this is here? Does this make sense that there is a negative relationship? If you increase the outflow, you'll ultimately have a negative impact on the stock level and vice versa. So if you increase the leak in the toilet, it will ultimately reduce the water level in the toilet. If you decrease the leak, it'll raise the water level in the toilet. Okay. So if I put those things together, this is my general inflow and outflow. And again, these are implicit links. So I've got them dashed here. We always have to remember they're there, but we'll typically not draw them. So we might draw, these would be explicit links like stock going back to the inflow, stock going to the outflow. This might be a population system where the number of fish in a population has an impact on its inflow and also an impact on its outflow. And what I want you to see here is that these are the correct feedback loop polarities. So over here, this might make sense to you that if I have a negative link going to inflow, there's an implicit positive link back to stock. So there's a balancing loop here because there's one negative link. What's often confusing is that there's a negative link from stock to outflow. This is a reinforcing loop. And that's because there's another negative link coming back into stock. And those two negative links create a reinforcing loop. So if you forgot about the negative link coming back here, you might not even see the loop. So does that make sense? Does everybody see these two loops? It's tricky if you're until you get used to looking at it. The online okay? All right, so the steps to adding these annotations. So here's a simple stock and flow diagram for our bacteria that's in Vensim. Let's say you draw it all black and white without annotations. The first thing you might do is say, are there consistent causal relationships that I can annotate? And I'd say, yeah, okay, as I increase average lifetime, it decreases death rate. As I increase death rate, it increases death. So as I increase bacteria, it increases death. So I could go through and I can label all of these polarities if possible. And then in my head at least, and then maybe explicitly at first, I can draw the implicit positive link from the inflows, and I can draw the implicit negative link from the outflows. So I add those two things in, at least while I'm analyzing this thing, and that will reveal loops. And so I can see, oh, there's a reinforcing loop here, and there's a balancing loop here. I might have missed that balancing loop if I didn't draw that thing coming back. So that's good that I drew those. But I have to keep in mind that most of my readers might be familiar with causal loop diagrams already. And the chart junk that's kind of here, like these implicit ones that I drew down here for my analysis, are going to maybe confuse them because there's like extra lines and they might be wondering like, since that's implicit anyway, why did you add it on there? Are you trying to communicate something to me? Is there something extra going on? So it's conventional to get rid of those. And you just have to trust that your reader who's familiar with stock and flow diagrams will understand that there's an implicit negative link here and an implicit positive link here. So this is the typical way, if we were annotating these stock and flow diagrams, how we would do it. So any questions about that? Like, do these links and loop polarities make sense? Questions online? All right, great. So for this simple example, we've got our stock and flow diagram for our toilet model here. And so if I want to generate a causal loop diagram based on this, then the first thing I do is I take all of my variables and I throw them into the causal loop diagram. And the causal links that are already here are easy to draw. Like here's the water level to tank gap. Well, here's water level to tank gap. Target water level to tank gap. Well, here's target water level to tank gap. Tank gap to flow water, tank gap to flow water. That's easy. But I have to remember when I'm drawing that CLD that there's an implicit link going from here to here. And so that's what I put into the causal loop. So if I convert a stock and flow to a causal loop diagram, then I definitely have to put in all of those implicit links that are left out in the stock and flow diagram. All right, so that makes sense to everybody. See the implicit links. An easy thing for me to throw at you at a midterm saying like, find all the loops in the stock and flow diagram. You have to make sure to look for those. Okay, great. All right, so we've got a few more minutes left here. So let me show you how to draw and simulate these things. I'll do a Vensim example here. I'm going to keep it short, and I'm going to try to do Insight Maker. If I can't do Insight Maker today, I'll start next time with the Insight Maker example. But there's video tutorials that are available on Canvas for both of these. So you can also take a look there. And for whatever reason, my Vensim video tutorials, like my most popular like YouTube video, I think it's gotten like, I don't know, 30,000 views or something like that in the last couple of years. So I don't know why. I think it tells me that Vensim or Ventana Systems needs better, documentation or something. But it's 10, 15 minutes long, so you can take a look if you think it will help. So let me pull up Vensim. And if you'd like, you can also pull up Vensim. Get the mouse back. Maybe I'll bite the bullet and stop the share. All right, so we're in Vensim here. Okay, and I think I've got the, so this is the new sketch environment. So I've mentioned to a couple people, if you have issues with Vensim stability or other things like that, it's a good idea to try going to tools up here and then down to switch back to old GUI, but we'll try it in the new one here. So now we're just gonna add a couple of buttons up here that we haven't used so far. So one of them is stock and the other one is flow. So if I want to create a simple like bacterial model, the first thing I do is click on stock, and I can go over here and I can type in like bacteria or number of bacteria or something like that. I'll make this a little bit bigger and maybe I'll go and change my defaults. We'll go up here. I think I right clicked and, oh, there's my defaults. It's over there. I just couldn't see it. So I'm just going to increase my font size a little bit for projection reasons. Okay, that's not so bad. All right, so bacteria now, so that's a stock. So it's drawn with a big box like that. I'll also add my flows. So I can click on the flow variable here. And I can, I click where I want the flow to start and where I want it to end. If the inflow doesn't have another stock that's connected to, I can just click on the blank canvas. And I'll save this. And it will put a little cloud there. And that cloud just means that this is an unlimited inflow. It's not going to pull from any other stock. So it's just kind of coming from out of nowhere. And I can call this births. And then if I want an outflow, I can click on the stock and click on a random spot in the canvas and call that deaths, like we've been doing. Any trouble with that? Anybody try? Whoever's playing along at home or whatever? Does this seem okay so far? The important thing to get to is the formulas, which we'll do here in a second. And then, even though the example that I did in the slide notes, I had the average lifetime and the birth rate. I'm just going to do average lifetime and then incorporate the average lifetime into this formula, as well as the average time between reproduction. So if I were to click on, again, I went to variable here, the A for auxiliary or variable. If I click on a spot and I type in average time to reproduction, and if I want to move that, get it off here, and maybe I'll move this down. And then I can also create another variable called average lifetime. And then I just need to draw links to make my formulas work. And so I know that my average time to reproduction sets the birth rate for the population. I know the average lifetime sets the death rate for the population. But I also know that the number of births depends on the number of bacteria that are reproducing, and likewise, number of deaths depends on that. So I have to draw those feedbacks as well. So I do bacteria goes into births. And remember, I can grab this little handle, curve it up. Bacteria goes into deaths. I can grab this little handle and bring it up. So that's pretty much just like drawing a causal loop diagram. And those are all the links that I need to make this go. And now I just need to put the formulas in. So any questions about any of that? Okay. All right, so now there's another button up here, equation, that we haven't used before. And by the way, in the new sketch, for those of you on these Macs that are having trouble right-clicking, there's this button they've added, appearance, which is the equivalent of a right click. And so if you click on that and then click on something else, it's equivalent to right-clicking that thing. So if I go to function or equation, this f of x here, when I immediately click on that, it changes the background color of anything that doesn't have an equation or whose equation is broken because of the addition or removal of a recent variable. And so I can now go up through here. I click on average time to reproduction, and it unfortunately put that on my other screen, so I need to drag it over here. And so this brings up this is new. This is our equation dialog in Vensim. And we can see which equation we're editing up here, average time to reproduction. And over here, there's a quick way to jump to all of the other equations if we didn't want to go back and forth. So if I were to click on births, deaths, it would switch to that equation. And it says here, this is a constant, which is true. The average time to reproduction, I'm going to go in and put in, I think we said the average time to reproduction was 0.75 time units. So I'm just going to put 0.75 in there. We'll actually deal with how to use real units after the midterm. For now, I'm just going to put this constant 0.75. And that's all I need to put there. So I can click OK. Now let's look at one that's more exotic, births. So this is an inflow. If I click on that births, brings up these equations here. This says type auxiliary. That automatically is filled in whenever a variable is coming into another variable because it's an auxiliary. It's going to be a formula, is basically what it's saying. And all of the things that come into it are listed in this box over here. So down here in this box, it says average time to reproduction in bacteria. Those are the two variables I'm allowed to use in this formula because of the links that are coming in. So I can click on them or type them in. So I can click bacteria divided by, I didn't mean to click bacteria divided by bacteria divided by average time to reproduction. And that is my inflow right there. It's just like bacteria divided by, I think I called it W. All right, so that's how I set up that flow formula. Any questions of that? You see, these are all the things that the inflows gave me access to. If they weren't there and I were to type them in, when I tried to run it, it would give me an error. It would say that, oh, that formula doesn't have access to that. Okay. So then let's look at average lifetime. Very similar to birth, it's a constant again. I'll put a 3 in there to match the spreadsheet. Go down here to OK. And then again, deaths. And notice again, it's got bacteria is going in, average lifetime's going in. So that should show up as being available for me to use. So I'll go to deaths. And so I do bacteria divided by average lifetime to give us my flow formula. And that's how I get the outflow. All right. Everybody good with that? Good. Then we can do the last important thing, the stock. Now, when you click on the stock, you never, ever, ever in this class touch this upper part of the equation where it says integ. That's automatically filled in for you by Vensim. So, and I want to emphasize this because this will come up in some of the first homeworks, whatever. People will try to update this formula. You never ever update that formula. Let Vensim do it for you as you draw the diagram. The only thing you update is the initial value. And so here, I'm just going to put in that there's one bacteria initially. See that down here, just this one here. Leave that alone. Let it Vensim do that. And then Vensim should be okay. So if I go down here and click OK, all of those black backgrounds are gone. The last thing I need to go do is go up to this model menu and then go to settings. And that is what, if I go to model settings, then in this tab, time bounds, I look here and it basically tells me what unit to use on my x-axis. And I think I don't want month there, so I'm going to change it to like seconds. So I'll pull down here and I'll say second. I can say how many, how long do I want to simulate it for? And I'll just do 5. And then here is my DT variable, time step. And so I am going to sort of match what we did in the spreadsheet. I'll just change that to like 0.001. Everybody see that? And just so we can at least get one sim out before we end here, I'll show you what happens when we run it. So I now have the ability to go up here and hit simulate, this little play button. And when I do that, it appears like nothing happens. But it just generated data, and now I need to tell it what data I want to plot. So if I go over here, I can click on, well, I can go up and I can select a variable, like I want to plot bacteria. Let's say I want to plot bacteria and births. And then if I go over and click on graph, now that those are selected, I just use the shift, by the way. I click on bacteria, I hit shift and clicked on births. And then if I click on this graph, then I can see both bacteria and births. I can turn off births or turn off bacteria, but I can see them growing just like they do in Excel. And that's great. But let's say I wanted to actually pull that into Excel. Well, what I could have done instead of graph is I can click table time down. And when I do that, if you look closely here, it's got a time column and it's got a bacteria column and a births column. This is exactly what you manually generated when you did this in Excel. And it's possible for me to go up, and I think in the new one here, if I go up to, I think, File, and I go to Save, I have to do this when I'm in this, I can actually save this as, bacteria.txt or something like that. And if I open this bacteria.txt in Excel, so maybe I'll see if I can open Excel. I don't want to go much farther than this, but let me at least open it in Excel, and then I'll let you guys go. If I think I just dumped that onto my desktop. I'm going to say that it is a delimited file, and I am going to tell it that it is tab delimited. It figured that out, put it into little columns. And so if I say finish, and then I bring this Excel over, then I get exactly the output that I would have gotten if I were to do this manually. But there's no formulas in there. But now I can use all the graphing tools in Excel to make even prettier graphs. So like I said, Vensim's just manually doing what you were doing by hand in Excel and dumping it out into a format that then now you can use in other tools to make even nicer graphs, but you can very quickly graph them in Vensim. All right, well, I'm going to stop there because I don't want to keep you guys any farther. I'm going to do that exact same example in Insight Maker at the start of Tuesday's class. But otherwise, read the chapter. And rather than bothering with attendance, I'll just give everybody attendance for today since I'm running a little behind. So have a good weekend. If you have any questions, feel free to come up. Anybody online who has questions, I'm happy to take them as well. Have a good weekend. All right, looks like everybody's off, so I will end the